Hey there and welcome to this video. Today I will talk about the embedding layer of PyTorch. I'm going to explain what it does and show you some common use cases. And finally, I will code up an example that implements a character level language model that can generate any text whatsoever. As you can see, I'm on the official documentation of PyTorch, and they describe the embedding layer in the following way. A simple lookup table that stores embeddings of a fixed dictionary and size. And what we can also see is that it has two positional arguments, one of them being the number of embeddings and the second one being the embeddings dimension. If I were to explain it in my own words, embedding is just a two-dimensional array wrapped in the module container with some additional functionality. Most importantly, the rows represent different entities one wants to embed. So what do I mean by an entity? One very common example comes from the field of natural language processing. There, the entities could represent all English words. Another example is categorical variables when working with tabular data. So if we have a category of color, the different rows would represent different colors. Note that there are also other non-deep learning approaches that one can use to encode categorical variables. For example, the one-hot encoding. To give you a real-world example, let me show you the Transformers codebase. Specifically, I will look into the architecture of BERT. As you can see, BERT is actually using multiple embedding layers, and for example, the first one, the words embeddings, encodes all tokens in the vocabulary. Note that this embedding layer is the very first block of the architecture, and during the forward pass, one provides the token indices, and this layer will simply output the corresponding embeddings. Let me now show you an interactive example. First of all, I instantiate the class without any keyword arguments. The representation shows us how we constructed the embedding. However, it does not show us the underlying 2D array. To see it, we need to access the weight attribute. It is a torch parameter, and what is important is that the requires grad boolean is set to true, which means that this entire array is learnable. Let me now prepare some inputs and run the forward pass. We see that the forward pass does nothing else than just querying the rows of the underlying weight array. Let us now try to use the keyword argument padding index. The row with the index of 5 is equal to zeros. Here I just averaged all embeddings and computed the gradient. As you can see, the gradient of the sixth row corresponding to the index 5 is zeros. That means that it will never get updated during the training process and it will always stay equal to 0. So if you're wondering what the use case of this padding index is, I guess one can use it for out of vocabulary tokens or unknown categories that are present in the dataset, but you don't care about embedding them. Finally, let me try to use the norm. The goal is to make sure that the norm of the embeddings is not too big, or in other words, that the embeddings do not move too far away from the origin. Here I selected the L2 norm and I set the maximum equal to 1. So here you are probably really surprised because the normalization clearly did not take place. I was surprised too when I saw this behavior, and it seems like one needs to first run the forward pass for the normalization to be applied. We see that the normalization was done. And also it was done in place for the weight matrix, however, only for the rows we queried during the forward pass. Anyway, I would say that the goal of setting the maximum norm is regularization and scaling. I am now going to implement a character level language model that uses the embedding layer. This model will be trained in an unsupervised way, and it will allow us to generate text. First of all, let me describe how one can generate the dataset. Let's say we start with the following string. We now need to decide on a hyperparameter that is called the window size, and let's say here I set it equal to 3. Alright, and now this is how we proceed. So we always take 3 characters and we try to predict the next character in the line. Note that this can be seen as a classification problem, and that's exactly the setup we are going to use. We will have a separate embedding vector for each character. These character embeddings will be fed to an LSTM network, and finally we will add a classifier as the last block of the network. Anyway, let's start coding. Let us start by creating the custom dataset I just described. Alright, let's go through the arguments. Text can be any string whatsoever, and it will be used to create our dataset. Window size is something we just discussed. However, let me also point out that the bigger the window size, the bigger our input tensor is going to be, and the more context we will actually be able to see. Vocab size will determine how many characters will be in our vocabulary, and if we stumble upon a character that is not in that vocabulary, we will just mark it with this tilde sign, which for the purposes of this video represents the out of the vocabulary token. Internally, we will create this character to index dictionary, and it will map any character to its position in the vocabulary. This will be just the inverse of the above. And finally, this will be all the characters that are in our vocabulary. First of all, we take our text and we replace all new line characters with spaces. We want to use a default dictionary because if we encounter a character that is not in our vocabulary, it will always be mapped to the last element. Alright, this one is a little bit messy and I apologize for it. However, all we do is to take the input text and we find the most common characters in it, and we find the vocab size -1, the most common characters, and we just create this character to index mapping. And then we just insert our most common characters into this default dictionary. And finally, we add our special out of vocabulary character to it. This dictionary is just an inverse of the character to index dictionary. And finally, we define the vocabulary for future convenience. The length of our dataset is nothing else than the length of the original text minus the window size. The goal of the getItem method is to construct the features and the target corresponding to a given index. To create the features, we take all the characters inside of our window and we convert them to the corresponding indices. To create the target, we do the same thing. However, we only do it for a single character that comes right after our window. All right, let us now implement the network. All of the integers above are hyperparameters. The vocab size and the embedding dimension are related to the embedding, together with the max norm. Hidden dimension and number of layers are related to the LSTM. And finally, the dense dimension is related to the linear layer. We call the constructor of the parent. Here we instantiate our embedding layer, and as described before, we will have a separate embedding for each character. Also note that we are using the padding index for out of vocabulary characters. create an LSTM layer that will act directly on the embeddings. And finally, we create two linear layers. The first linear layer is going to take the hidden state and map it into a new space. And the second linear layer is going to output the logits over all characters in the vocabulary. Let us now define the forward pass. The X will represent the characters in our window for each sample. H and C will represent the hidden state of the LSTM, however, they do not have to be provided. This function will return logits that can be turned into probability distributions with a softmax. And finally, the updated hidden states will be returned too. We take the indices of the input characters and we run them through the embedding layer, and that is going to give us the embedding vectors. Here we take the character embeddings and we run them through an LSTM network. We average over all layers. We use both of our linear layers, and at the end, we end up with logits. So this function takes in a loss callable, a network, and a data loader. And it goes through all the batches in that data loader, and it computes the losses, and then it averages them. Let us now write the last utility function that generates the text. Alright, so we give this function the number of characters, our trained network, and also the data set, and it will generate an arbitrarily long text. Here we enforce that the initial text is not empty. Here we initialize our result with the initial text, and we set the network to evaluation mode, and finally we set the hidden states of the LSTM network to none. If we want, we can specify the random state and get reproducible results. If this is the first iteration, we take the entire initial text and turn it into features. However, if it's not the first iteration, we will just take the last character. To run the forward pass, we get our logits and the hidden states. We turn the logits into the probabilities, then we sample a new character, and finally we add the new character at the end of the resulting string. Alright, now we have everything we need and we can write a small training script. We read some text from a text file, and then we define the hyperparameters of the model. Let me just point out that I'm setting embedding dimension equal to 2, and that is because I want to visualize how these embeddings evolve over epochs. If you wanted to build a model that generates realistic text, I would definitely increase the embedding dimension and other hyperparameters. However, for our purposes, this is great because it will allow us to visualize. We are going to use the cross-entropy loss because we are dealing with a multi-class classification problem. We instantiate our dataset. We split our dataset into the training set and the validation set. We create the train data loader and the validation data loader. Each of them will be sampling randomly from a disjoint subset of the dataset. We instantiate our network. We instantiate our optimizer. Here we prepared a list that will be used to store the character embeddings after each epoch. Here we implemented the standard torch training loop. At the end of each epoch, we will compute the average training and validation loss. We will also generate some text using our network, and that will allow us to monitor whether the model is getting better. We will create a pandas data frame that holds the weights and also some additional metadata, and we just append it to our embedding history. Finally, we create a big data frame that concatenates all the per epoch ones, and we save it into a CSV. Note that I'm not saving the model weights because I don't necessarily care about them. The main point of this tutorial is to show you how the embeddings evolve over the training. Let's see whether it works. As you can see, I downloaded the Dracula book, and we will use it as our training set. Note that I'm not running this on a GPU, so this will take some time, and I will just cut to the end for you. All right, so we trained the model for a couple of epochs, and the training and the validation loss were going down. When it comes to the generated text, it's by far not realistic. However, the model is definitely better than a random character generator, and it does have a basic understanding of the English characters. I created a small visualization of the results in a Jupyter notebook. Since we set the embedding dimension equal to 2, we can visualize in a 2D plane what the embeddings were after each epoch. Another approach could be to use higher dimensional embeddings and then do dimensionality reduction. However, this 2D example is easier to explain. Anyway, let me point out 3 important facts. If we focus on the origin, we see the tilde sign. As we move across the epochs, it does not move. Another important thing is that all the embeddings lie within the circle of radius 2 from the origin, and that is because we specified the maximum norm. Lastly, we see that before training, the embeddings were just randomly initialized. The most radical rearrangement happened after the first epoch. The numbers, for example, were already put into the same cluster here. As we continued the training, the characters that are somehow similar started to group themselves together. If we look at the last epoch, we see many cases of 2 character groups containing the lowercase and the uppercase version of the same letter. For example, the letter T, the letter Y, the letter H, the letter P, the letter O, and so on. Clearly, these embeddings are not perfect, and there are also a lot of letters that were not grouped at all. Just to give you some context though, the transformer-based language models are using hundreds of dimensions for their token embeddings. Anyway, I find this toy example really instructive. Finally, let me remind you of the amazing fact that we trained this model on a downstream task of predicting the next character in a string, and the model learned these meaningful embeddings completely on its own. Anyway, that's it for the video. I hope you enjoyed it and that you learned something new. If you have any suggestions or comments, I would be more than happy to read them. And I guess have a nice rest of the day and see you next time.